Hi students. So today we begin Math Question Bank 22 and today I'm going to discuss two questions which are focused on least square exponential curve fitting, and these questions are very important in data science. Any problem related to data, least square and so on, we are going to do this problem mathematically, and we are also going to use Python to check our results. So that's something which is going to be useful to you if you are somebody who wants to ask students questions related to data science or anything to do with data or curve fitting. I'm Dr. Ganguly. So let's start with this question. Now I have discussed this in the previous question bank, but I am going through it very quickly today because this is going to be the basis of the question 2, which is more complex and more accurate version of the exponential least square fit. So essentially we have three data points 1, 2, 3, and for each of these data points the xy coordinates or data is given. So for 1 it's x is 1, y is 3. For data point 2 x is 2, y is 4, and for data point 3 x is 4, y is 8. Now one of the standard ways which is used to solve these kind of problems is to take this exponential curve fit and to essentially take the log on both sides. So what this does is that it linearizes this particular problem. So of course we use the symbol y hat here to demonstrate that this is an estimate of y. The actual values of y's are known as the three data points here. Y is 3, 4 and 8, and y hat is the estimate which is known for all values of x. Now if I take the log on both sides, I get log y hat is log a plus bx, and I can write this as z hat is mx plus c, which is the equation of a straight line. Now z hat is equal to log y. I compare this equation with this equation. M equals b, you can see that here, and c equals log a. So essentially if I am able to calculate m and c, and then I can get the values of a and b from these relations here. Remember also that z is log y, so for all these particular values of y, I actually have to calculate z and I have to fit the straight line. So let's try to do that. We have the three data points here. We also have the values of z as the log of the value of y. So essentially I get three equations involving z1, z2, z3, all hats or estimates, and I can write these as mx1 plus c, mx2 plus c, mx3 plus c. Now I substitute x1, x2, x3 as 1, 2 and 4 respectively, and I get this equation here. Now, corresponding to each of these estimated values, I can calculate the residuals at these three data points. So these are epsilon 1, epsilon 2, epsilon 3, and the residuals are simply the values of z, and we have to subtract the values of z hat. So for example, for the first point here, you would have log 3, which is the value of z here, minus m minus c, because z1 hat is m plus c. Similarly, for epsilon 2, I get log 4 minus 2m minus c, and for epsilon 3, I get log 8 minus 4m minus c. This should be 3 here. This is a typo. So now I can get the value of L, which is an objective function, which is the sum of these squares. So essentially the residual epsilon 1 square plus epsilon 2 square plus epsilon 3 square. That's what's written out here. So this is the mean square, and this is something we are going to minimize. So that is why this method is known as the least square method, because we are trying to minimize this particular function. Now, of course, you can realize that this function is nothing but a simple mathematical function, and it is a function of m and c, or two variables. So from calculus we know that if we want to find the minimum point, we have to set the derivative with respect to c and m to 0. So that's what I have done here. If you take the derivative and set it to 0, you would get a 2 here, and then you would be differentiating with respect to c, for example. So each case you would get a minus 1. Now I can simplify this and I can get this equation in pink. Similarly, dl by dm, I get this equation here. Here you are differentiating with respect to m. So you are getting a minus 1 here for this one. For this second term, you are getting minus 2. And the third term, you are getting minus 4, because each of these terms is getting differentiated with respect to m. Now I get the second equation here. These two equations in pink are simultaneous equations. I can very easily solve them and I get the value of m as 0.3297 and c as 0.75. Now, of course, you remember that from this m and c, I can calculate a and b because there is a relationship. For example, c is log a, so a would be e to the power c, so a comes out to 2.1213, and m is b, which is 0.3297. Now, I have just retained all the decimal points here, which I got from my calculator. It's not necessary, but it looks good. Now I have this solution here. I have obtained the values of a and b. So I immediately obtain the curve fit to be y hat is 2.1213 e to the power 0.3297x. So this is the problem which you can very easily solve. Now let's just check this. Let's check it in Python. So in Python, what I can do is I can import NumPy, I can import SciPy, I can define this particular data point out here, and then I can try to curve fit a straight line through this particular set of points. And you can see I have obtained the values of m and c here, which are printed out. So m is 0.3297 and c is 0.7520. And again, like in the previous slide, the transformations I showed you, after that you would get this particular value of y hat, which is exactly what we have obtained through the laborious derivation. Now, interestingly, if you were to put these 3 points in Excel and ask it to fit an exponential trend line, you are going to get the exact same formula which we have derived before and which we have obtained in Python by proposing a log type of linear fit. Now, it's interesting that Excel is using this method to solve this problem. But we are going to actually use a more detailed method in question 2, and that's going to show you some of the importance of the nonlinear aspects of problems here. So question 2 is essentially you again fit a, e, b, x through the following data, but now you tell the student that do not use logs. So this is going to throw a curved ball or googly at them, and then they are going to have to use the exponential functions directly. So what would happen in that case is that the mathematics of the problem, at least in the formulation, remains simple. In fact, it may be simpler than in the previous case because exponential notation is more compact. So what you get here is y1 hat is ae bx1, y2 hat is ae bx2, y3 hat is ae bx3. Now x1, x2, x3 are 1, 2 and 4. I substitute that here. So these are the estimates of the y values. Now for each of these three cases I can get the residual. So of course I know the value of y1 is 3, y2 is 4, y3 is 8, and then I subtract the residuals which are obtained in these three equations here, which are given in black. So I have the three residuals at the 3 point and I can form the objective function here as L, which is the sum of the square. So each of these terms here, 3 minus AEB square plus 4 minus AE2B square plus 8 minus AE4B square. These terms are listed here and this is the objective function. Now, of course, if I minimize this function, I will be able to get a and b, and then I can form this curve fit here directly. So there is no transformation here to z and taking the log and so on. So let's take this function and we are going to differentiate it. So first what I do is I differentiate it with respect to a. So if I do that, I get this equation here. So remember, in each case what's going to happen, you're going to get a term like 2 into 3 minus a e to the power b, and then I have to look inside this particular bracket and I have to differentiate this with respect to a. So I'm going to get minus e to the power b. Similar thing is going to happen in these two terms, and in each case I'm going to get minus e to the power 2b and minus e to the power 4b. That's the coefficient of a is going to come out in these particular expressions. So now I have this expression, and of course I can set it to 0 because I'm looking for the minimum point. Now if you look at this expression, I can cancel these two out because they are common to all these three terms, and I can cancel the negative sign out also, which is in front of the e term here or the exponential term here. Then I can expand each of these terms. So the first term would become 3 e to the power b minus ae to the power 2b. Similarly, the second term would become 4e to the power 2b minus ae to the power 4b, and the third term would become 8e to the power 4b minus ae to the power 8b, and this entire thing equals 0. So I can write this out in this form if I take all the terms involving a to the right hand side. So that's what I've done here. The terms which have a in them, they have been taken to the right hand side, and then from this equation here I can immediately solve for a because a is common to the terms in the right hand side. So this equation in pink is the solution for A. Now here I have been able to make one breakthrough, that is I have been able to get A in terms of B. So now if I calculate B, I can immediately get A. So I need one more equation. So what I do is I go back to the objective function L, and this time I differentiate it with respect to B. So in this particular case, again, I will get the derivative here, and in each case I will get the term 2 into this expression here, and then also I will have to differentiate this term inside the bracket with respect to B, which is going to give me minus AEB in this case, minus 2AEB in this case, and minus 4AE 4B in this case. So this is the expression I get, and I can immediately simplify it. I can drop these two terms which are common to each of these three expressions. I can also drop, for example, the negative A terms which are common to these three expressions, and then I can simplify each of these terms. So the first term, for example, becomes 3e to the power b minus ae to the power 2b. So remember, there is a eb here, there is a eb here. So I can add the exponents and I can write e to the power 2b. Similarly, I can simplify this term, I can simplify this term, and this entire thing becomes 0. Now what I do is I take all the terms involving a to the right hand side. So I bring it here, and then I substitute the value of a which I obtained in the previous slide here. Remember that equation in pink? I have simply brought it here. I have copied and pasted it here. Now what I do is I take this denominator of this pink term to the left hand side and I keep the numerator. So I essentially end up with this complicated looking equation here, where I have some expression on the left hand side is equal to some expression on the right hand side, and you can see that this entire term is composed only of functions of b. So that's one progress we have been able to make. Now the algebra gets pretty cumbersome. What I have done is I have taken the left hand side here and expanded it, and I have taken the right hand side of this equation and expanded it. So this is just a simple multiplication, so you have to just do it very meticulously and fastidiously. Means you have to take this term, for example, and multiply each term by the coefficient here. Like that you have to proceed. So after I do that, I slightly simplify these expressions. So there is some common term here, and I get this LHS and RHS, or left hand side and right hand side, as these two equations in pink. Now of course I can write that these two are same, and if I do that, the LHS equals the RHS, then I get some further simplification and I get this equation in blue here. Now if I look at this equation in blue, I can take e to the power 4b out and I can set the remaining to 0. So I do that here and I get this equation in red. Now you can confirm it. In fact, I was somewhat perturbed that I may have made some error in this, but I will show you at the end what result I got in Python, and the result is completely correct. So looks like this mathematical calculation is correct. You can check it out and see yourself also. It is certainly an exercise in exponentiation and multiplication. You can set it as a sub problem also in any exam, for example. So now one of the simple ways you can do this problem is to find the root using the traditional way of plotting a function or graphing a function. So this is what I have done here. Now if you are conducting an interview in Zoom or Team, you can ask the candidate to plot this function in Excel. So actually I started with some numbers like minus 10 to 10, and then I found the root, and then I further zoomed down to the root, and I have plotted here from b is 0.33 to 0.34. This is how the function looks. So you can clearly see the root lies between these 2 points, 0.33 and 0.34. That is the value of b. So now I have done some number crunching in Excel. So what I did is I looked at different points in the vicinity. So I have tried to bracket the root here. And at the end of this particular exercise, I got B is 0.3352145, which is good enough for most work. Now, as soon as I get B, I can immediately go to the equation in pink, which was A, and I can get 2.089197. So now I see the curve fit which I have obtained, y hat is 2.0892 e to the power 0.3352x. You see, this approach which we took in the second problem is slightly different than the first problem. Now, most things such as Microsoft Excel are going to throw this particular log type of solution to this problem, but the no log solution is different. But we are going to check the veracity of this solution pretty soon. So of course I solved this problem using Microsoft Excel approximately, but let us try to solve it using Newton-Raphson method. So if I take this equation FB, I can find the derivative. Remember, in Newton-Raphson we need the derivative. The Newton-Raphson formula is essentially given as x1 is x0 minus fx0 by f dash x0, where x0 is a starting value or initial guess. Now, of course, the first iteration proceeds like this, and then after that you can calculate xk plus 1 is xk minus fxk by f dash xk. So we are going to check the values in these cases, the log and the no log cases, and we are going to use the log case as the starting point to solve this problem. So here I have done this in Python. I have written a very simple code using Newton-Raphson method. So essentially first I have to import NumPy, and then I simply form this while loop here. I start off with x0 value from the log side, that is 0.3297. Remember, we are only dealing with B here. We have the while loop. Now in Python, that is a very simple way to call the function, that is the lambda property, and then again I get f and f prime here. So you have to cumbersomely type out that particular equation in Python. I've used Google Colab here. It's free. You can check it out and practice Python in Google Colab. It's very nice, and it also saves all your work in Google Drive. So that's another advantage. I just coded in the formula for the Newton-Raphson method here, and then here I have printed the output. So you can see very quickly Newton-Raphson is converging to this value 0.3352, which is the value which I obtained for the case with no log, and that's the result we have obtained after our enormous calculations. So at least the solution of the method is correct, or the solution of the equation is correct. But we don't know whether the whole procedure we have done is correct or not, because there is always a possibility of algebraic mistakes when you are doing so many cumbersome calculations. So here actually I have tried to fit the curve directly using Python. So I've imported NumPy and SciPy. I have defined the two data sets x and y, and then I have simply invoked the curve fit function with this particular exponential curve fit here. I also have to give a starting value here. So I have given the starting value from the log approach or the previous approach, which is obtained from Microsoft Excel. And you can see here the solution. I get the solution which I obtained here exactly. So this is very pleasing, because it means that all that algebraic manipulation is correct, and so you can also obtain this in Python. Now of course many people feel that they can easily do these things in Python or any other programming language, but especially Python. So why bother with all the math? But then it's good idea to know how these algorithms are working, because somebody has actually written the code to solve these problems, and so one should know actually how this problem is being solved, at least somebody who is saying that he claims to be a data scientist. So now just to show you that you could start from some different point also, we don't just have to start from that previous solution of the log problem. I have started here from 2 and zero point 0.5, and again I obtain the solution which we obtained before. So this is the same solution, but the starting solution here is different. So again here also the Python SciPy module is using some kind of algorithm to do this problem, and it's basically solving it numerically. Now, just to revisit a problem which we did in our previous question bank, where we fit a linear curve through this data, and again we also use Excel to get that. That also you can do in Python very easily using the SciPy curve fit function. Now with the linear curve, you don't have to give any initial guess, but you do get the same solution here. So as far as the values of m and c are concerned for the straight line, I'm getting the same values here. You are getting this 1 and 1.7143. This 1.7143 is the slope and 1 is the intercept c. Now remember again, Excel trend line gives me the same result here. So lot of these problems can be very easily done using Microsoft Excel, or they can be done using Python, and most people tend to do it. But today what we saw in the question bank is that the math is behind that, and the math is basically calculus. It is basically optimization. And so many people say that actually optimization is at the heart of data science, not only in more complex things such as machine learning, deep learning, and so on, where you are using stochastic gradient or something like that, but even in the case of simple least square fit, it is nothing but an optimization problem, a function minimization problem. And of course, it has been coded into computer, so that makes your life very simple. But if you are a teacher, if you are a professor, if you are somebody in the STEM field who wants to grill some candidate out there, then these questions are going to provide you good background. Now, do remember that many people are not going to be able to solve this problem completely in a class or in some kind of interview setting, because there is going to be a lot of stress on them. So what you can ask them is to actually do some of the procedures and show how this could be done. You could also ask them to actually do this problem in Excel or Python, and then try to give the fundamental understanding behind how this problem was solved, so that they do not think that what's happening is that there is some black box built into SciPy and they are simply using it. They need to know as to how these equations are actually getting solved and how the numbers you are obtaining are actually coming out. So it's always a good exercise to do some problems like this at least once in your life.